Welcome to Frank Stajano Explains. Today's topic is a Discrete Mathematics exam question walkthrough to accompany my Lent-term lectures on this topic, which you can already find in the relevant playlist on this channel. If you find this material helpful, then I really appreciate it when you stick a like on the video. I post weekly, so subscribe and hit the bell, you know the drill. The way to get the most out of these exam question walkthroughs, and there are a few others in a dedicated playlist, is for you to pause the video on the question, remove all other distractions, and then attempt the question on your own in 30 minutes, with closed books and no internet, same conditions as the people who actually did the question when it was set, as seriously as your final marks depended on it. If you solve the question well, then watch the video. If you can't solve it, then don't watch the video yet, but instead study the relevant theory and then leave the question aside for a day. And try it again the next day, again with closed books in the same conditions. At that point, you are extremely likely to experience a light bulb moment and be able to solve the problem. My mentor, Professor Mencoccini, taught me this recipe when I was an undergraduate, and it works really well. More on this in another video. So anyway, here is the exam question. Stop the video and do it by yourself. Then come back. Stop the video, seriously. If you keep watching, you'll spoil your only chance of solving this question from a virgin state. New questions, new to you I mean, are rare and precious practice material, so don't waste them. Okay, welcome back. I assume by now you've done the question for yourself, so well done for that. Let's have a look at it together. So the question has two parts, A and B. For each symbol x in the alphabet sigma equals ABC, let O of x be the language over sigma consists of all the strings that contain an odd number of occurrences of the symbol x, and let E of x be the language of strings over sigma containing an even number of occurrences of the symbol x. So the first sub-question in part A is give a deterministic finite automaton whose language of accepted strings is OA, the language of all the strings over ABC that contain an odd number of A's. Okay, well that looks pretty easy. If I consider the parity of A's in a string, that's basically only two possible states, an even number of A's or an odd number of A's. And I should remark, because I have been surprised to hear that a number of my students thought otherwise, that 0 is an even number. Okay. Obviously, I say, well, 0 is an even number, 1 is an odd number, they alternate odd and even, so 0 is an even number. If you have no A's, then this belongs in, a string with no A's belongs in E of A, and a string with 1, 3, 5, and so on A's belongs in O of A, which is the set we are going to recognize with our deterministic finite automaton. So I'm going to have a state called even, and another state called odd, and I start in the even state because the empty string has no A's, and then whenever I get an A, I go to the odd number of A's state, and whenever I get another A, I go to the even number of A's state, and whenever I get any other allowed letter that's not an A, that is a B or a C, I don't change the state. So if I was in here and I get a B or a C, I stay there. And if I'm here and I get a B or a C, I stay there. And if in the end I get an odd number of A's, then I accept the string. Otherwise, I don't. And that's all I need to do to recognize the strings with an odd number of characters. That was easy. Now, sub-question 2. Give a regular expression whose language of matching strings is OA, the same stuff as this. This is only two states. Let's see if the regular expression is equally simple. So I have to have either no A's or an even number of A's. So I'm going to repeat the A two times. So I'm going to say A, and then you can have any garbage you like other than an A, so B or C repeated however many times you like, and then an A. But this thing, I'm going to say you can have it you can have it 0 or more times, so I would put brackets around it and an asterisk. However, I'm going to first add some more b c star here before I close these brackets and put the asterisk, because otherwise when I repeat this thing, this a here would be adjacent to this other a from the next bracket, and I want to allow for other things in the middle to be there. Now, as written, this thing would only allow things that start with an a, if they start at all. So I would want to also put b or c asterisk in front of that. So I can do anything I like with b's or c's before I encounter the first a, and I may never encounter the first a if this one never happens. And then if I have an a, then I can't get out of this bracket without having another a at some point, regardless of all the other garbage I do before and after. And then I can keep repeating that, and because this ends with, if I want to, more b's and c's, then I think that I've covered all the cases in here. So that was also easy, although rather longer than I expected, seeing that this thing only had 2 states. I have no idea if this is a minimum expression. This is what comes naturally, to me at least. Okay, so the third sub-question. Give a deterministic finite automaton, okay, one of those, whose language of accepted strings is OA intersected with EB. So this means give me an automaton that recognizes all the strings that have an odd number of A's and an even number of B's. So an odd number of A's I've already done here. And it's basically saying in here, instead of just ignoring what happens to the B's, you should have another similar automaton to this one with 2 states inside this state, so to say, that checks how many B's you have. So what I do is basically I arrange these as a kind of matrix. So in this direction I look for the A's, and in this direction I look for the B's. Regardless of what I call them, I'm going to have 4 states like this. I'm going to start in here, and if I get an A, I go here, and if I get another A, I go back here, because to the left of this line over here is when I have even A's, and to the right of this line is when I have odd A's. But this also happens here. Okay. On the other hand, if I am above this line, then I have even B's, and below this line I have odd B's. So when I get a B, I go here. When I get a B, I go here. When I get a B, I go here. And when I get a B, I go here. So I'm not going to bother naming those states, but this is the state where I have even A's and B's. If I get one B, then I go here. These are the states where I have odd B's. These are the states where I have even B's. Those states where I have even A's. These are the states where I have odd A's. And I was asked to recognize the strings that have odd A's, so on this side, and even B's, so on this side. So this is the state that has the odd A's and even B's. And that, if I did just that, I would not get the full marks, because this is not a deterministic finite automaton over the language ABC, because it doesn't say what happens when I'm in a state and I receive a C. Of course, what happens is that I should stay in the same state, but the automaton is incomplete without these loops that say C on every one of the states. C, C, C. So remember, a deterministic finite automaton has to have an answer of where to go from any state for every symbol of the alphabet. If this is not the case, you have not done a deterministic finite automaton, you've done a non-deterministic finite automaton, and if the question asked you to do a deterministic one, then you will not get all the marks for that question, because your diagram does not match a DFA. And that is an oversight that matters in a course like this one, where we have to be extremely precise. Okay, so I've done my first 3 questions. I dispatched part A, and that sounded pretty easy to me. Now, what's part B? M equals blah 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 is a deterministic finite automaton whose set of states Q has L elements. Okay, suppose that M accepts a string W in sigma star whose length of W satisfies that it's at least L. The length of the string is at least the number of states. Show that W equals U1 v U2 for some strings U1 v U2 in sigma star, such that the length of U1 is strictly less than L, the length of that string W. The length of V is between 1 and L included, and M accepts U1, V, and U2 for all n in the natural numbers. And that is obviously the pumping lemma, and so this is basically saying, can you reconstruct the pumping lemma in an exam question setting, which is not the type of question you would get if you were doing an open book exam, as may be the case during COVID. So this was an exam question that was set in invigilated conditions where you had nothing other than your paper and your pen and possibly a calculator, which would be totally useless in this discrete math setting. It's still good practice for you to do these exam questions in closed book settings and see if you can reconstruct the theory when a past question asks you to do so, because it demonstrates that you actually understand and know it and have it ready to mind, instead of having to look it up before being able to reproduce. All right, so let's see if I can reconstruct a proof of the pumping lemma, pretending that I was doing so in an exam setting based on this question over here. So my automaton M has L states, and it accepts a string W of length at least L. Okay, so if I write down W as a sequence of symbols of at least L symbols, so it's going to be A1, A2, A3, AL, and then possibly more, up to some call it M, since I'm already using N for something else. Then, if this string is W, which is at least L items long, then this string, starting from the first state, which I'm going to write as Q0, it's not the name of the state, it's an indicator of the state, and then the next one, following the A1 symbol, is going to transition me to another state I'll indicate as Q1, and then A2 is going to take me to Q2, A3 is going to take me to Q3, blah blah, AL is going to take me to QL, and AM is going to take me to QM. Now, clearly, since this sequence contains L plus 1 states, and there are L distinct states in my machine M, then at least 2 of these states are the same state. So any 2 of the states in this part of this sequence of states, this part up to L, that are the same, I can designate with 2 special letters. Let's call them, say that one of them is QX and another one of them is QY, with the property that QY is equal to QX, because there has to be at least 2 in this sequence that are the same. There can be more than 2, but anyway, there can be several pairs or triplets or whatever. Anyway, there's at least one state that's repeated, and let's take any of them within this first L. Then I'm going to define the part of W that takes me from QX to QX again. I'm going to call it V. The part of W that takes me from Q0 to QX, I'm going to call it U1, and the rest I'm going to call it U2. So suppose that M accepts a string W made like this, whose length satisfies that it's at least L. And we can see it's L, and there could be more over here. Show that W is made of U1, V, and V2, and U2, and I told you how to split it into this on the basis of where there is a repeated state. That's the boundaries of V. And then U1 is what's before, and U2 is what's afterward. Such that U1 is, the length of U1 is less than L. Well, it is because there's the sequence of states here. There's L plus 1 states and L transitions, and I'm saying that there is a cycle, so this cycle being non-empty, otherwise I wouldn't see that there's two states that are repeated. Then this thing contains at least one symbol, so this means that this contains fewer than L symbols, so this satisfies that. V is at least one symbol, as we just said, and less than L symbols, because that's also included in this part. And M accepts U1 V to the n U2 for all exponents of V in the natural numbers, because, well, clearly this string is accepted by definition over here, and if V takes me from Qx back to Qx, then if I reapply V another time, it will take, starting from Qx, it will take me back to Qx, and if I apply it another time again, it will take me back to Qx. So this means I can repeat this V as many times as I want, and then I continue from Qx with this U2 sequence. It will always take me to the final state, which is an accepting state. So if this string was accepted, then any string obtained by repeating this as many times as I want, including none, will have the effect that once I get to Qx, then however many times I return to Qx, then I can go from Qx to the accepting state with U2, and so that's fine. And so I basically proved this theorem. Now part B2 instead is somewhat more creative. It's not a textbook result, and so it requires you to have understood the pumping lemma in somewhat greater depth, so that you are able to derive an additional small result. Okay, what is it about? Hence show that if infinitely many strings are accepted by M, which they are because I can generate infinite strings using this pattern, then it, M, must accept some string W prime with a length between L and 2L. Well, this sounds intuitively fine, because this pattern generates all sorts of things with all sorts of strings whose lengths differ by the length of V, and the length of V is bounded by L, so one of them must end up between L and 2L, I would imagine. But that's not a rigorous argument, because W, our starting thing over here, could be expressed as U1 V U2, and while it's true that U1 and V together were within length L, U2 was unbounded. It could be much longer than L as far as we know, so it could be that even if I remove V, then U1 U2 is actually much greater than 2L. It's somewhere over here. Let's say, I don't know, 5L, whatever. And if that's so, then pumping it further will just keep me further to the right, but I will never be able to hit the space between L and 2L. So I must give a more rigorous argument that there is always going to be a string accepted by M in this interval between L and 2L. How do I do that? Well, let's try a proof by contradiction. There's going to be infinitely, well, if there are infinitely many strings, and we know there are infinitely many strings, then there are infinitely many strings accepted by M that are of length at least L, because the ones of length smaller than L are an infinite number. So of all these strings that are of length greater than or equal to L, let's consider the smallest, and let's call it, let's say W0 is accepted by m is of length at least L and is shortest, the shortest string that is accepted by m and of length at least L. Shortest of all these. And let me see if I can derive a contradiction if I also assume that the length of W0 is at least 2L. Okay, so I want to prove that it's not possible for the shortest of these strings accepted that are at least L long. It's not possible for that string to be of length greater than or equal to L. So let's see if we can derive a contradiction by having added this condition to these ones. W0, because W0 does these things in the bubble, then it matches the conditions of this theorem in b.ii, which is the pumping lemma. And so it must have this form over here. So W0 can be expressed as U1 V U2 for some U1 V and U2. And it must be the case that U1 V to the 0 U2, which is U1 U2, is accepted by M by construction. So now what's the length of this U1 U2? Either this length is less than L, strictly less than L, then if it is strictly less than L, so I said this is accepted by my automaton M. Because it's strictly less than M, it wouldn't be an example of these that are between these two. But if I add one more cycle, then it would be. So U1 V U2, the length of this would be something less than L, plus L would be strictly less than 2L. And it would also be greater than L. And so, well, would it be greater than L? If it weren't, I could make it greater than L by adding more instances of V, because V is less than L, and so I'm able to add as many as I need without exceeding 2L. So in this case, I have obtained a situation where this string, since this string U1 V U2 is shorter than this, it's shorter than W0, which was supposed to be the shortest. So this is a contradiction. So this case cannot happen. So in this case, U1, U2 must be greater than or equal to L. Now, if U1, U2 is of length at least L, then it matches this part. And because it is clearly shorter than W0, because I dropped V symbols from it, then it is not true that W0 is the shortest anymore, because there's another string that is accepted by M, because this is accepted by M, is greater than or equal to L. That's our hypothesis in this branch. And it's no longer true that W0 is the shortest, because this is definitely strictly shorter than W0. So this is also a contradiction. And so this means u1, u2 cannot be of length less than L, cannot be of length greater than or equal to L, and so it's impossible for this situation to exist. And this means I cannot add this condition without always incurring in a contradiction. And so this means that it is not possible for the shortest such string to be 2L or more. And so there must be one at least that is in this interval. So this is, to be honest, something where the thing you want to get to is relatively simple, but it's pretty easy to get entangled if you're trying to prove it rigorously. And in fact, when this exam was set, only very few candidates could give a convincing proof of this part B2. So I would recommend practicing on proving these additional results rather than just memorizing bookwork style proofs. Obviously, in an open book exam setting, as you are likely to get under COVID situation, you would never get this style of questions because it would be worth nothing asking you. And so this style of questions would be more likely and would be worth more marks. So it's worth you being prepared. So if you enjoy this type of content in these videos, find it helpful for your preparation for this course, then please stick a like on the video. And because the YouTube statistics tell me that most people actually stop watching before the end of the first minute of my videos, then if you are in the elite minority who got all the way to here and you are hearing what I say, then please leave a comment below mentioning the secret code word krotsa, and I'll be delighted to find out that someone was still listening. Now, we seem to have had recently a few people who ask questions that are completely unrelated to the video, such as, what subjects should I choose for A levels? And I tend not to reply to these anymore if they're not on a video that talks about admissions. But if you ask me something relevant to the video, kind of questions that a student attending in person would ask me at the end of the lecture, then rest assured I will reply. And if it is something that's pertinent to the content, if it's a genuine question you had after having engaged actively with that material, then fear not, no question is considered silly, and you can ask it anonymously anyway, and I will reply. I'll reply publicly for everyone's benefit. So I hope you enjoyed this, and until next time, see you.